What we're going to go over in this video is simplifying nth roots. So first off, what I mean by nth roots is n is the index, okay? So we're talking about a radical, and right, x is the radicand. So the nth root is, you could be taking the third root, the fourth root, the fifth root, and so on. And it's going to be an integer value, okay? It's going to be greater than or equal to 2. When you don't see one, it's the second root, right? So the square root of x, what is n? N is 2. If you had the cubed root of x, what is n? 3. If you had the fifth root of x, what is n? N is 5. Okay, so you'd be taking the fifth root of x. So what we're going to be working in this unit, okay, it's not only having constant factors, but having variable factors. That means it has the ability to change based on what you plug in. So when we simplify, okay, with variable factors, it's a little different than simplifying with constant factors. Okay, so if I ask you to simplify the square root of x squared, okay, you have the factor of x 2 times. So if I'm taking the square root of x squared, okay, well, I have the same factor twice, so they undo each other, so that's going to give me x. If I have the square root of x to the fourth, okay, I have the same factor of x 4 times. So essentially, I've got x squared times x squared, or I could think about it as I've got x squared to the second power. And so the index and the power of 2 undo each other because you've got x squared twice. And so the power of 2, this power of 2 and this index of 2 undo each other, leaving you with x to the second. If I ask you to simplify the square root of x to the 6th, I've got the same factor of x 6 times, okay? You can simplify a second root if you can raise it to the second power. Can you take x to the 6th and write it as something to the second? Yes, you could write it as x to the third. That is going to leave you with x to the third. That's because I can write this as x squared times x squared times x squared. How many times can you simplify that? Well, I could break this up to be the square root of x squared times the square root of x squared times the square root of x squared, which would simplify to be x times x times x, which would give me x to the third. What would I do in a situation like this? Well, square root of x to the third, okay? I can simplify this because this is the same as having 3 factors of x. And if this is a square root, I just need 2 factors in order for this to simplify, but I'm going to have a leftover factor of x. This is going to simplify to be x square root x. And if I have the square root of x to the 5th, well, I really have x times x times x times x times x. I've got that x squared, I've got that x squared, I've got one leftover x, right? This is going to simplify to be x squared, square root of x. But we don't want to do this every time, okay? So let's do one more, the square root of x to the 7th, okay? That would be x times x times x times x times x times x times x. I've got x squared, I've got x squared, I've got x squared. Okay, I've got this times x. If I simplify each of these, the square root of x squared, this would be x, x, x. That would be x to the third, and I'd have one leftover factor of x. So if you notice, see how I did here? Try to get it to the second, to the second, to the second, okay? When you have your variable factors, you want to try and make it so that you have, if you have the cubed root of something, okay, you want to try and get it something to the third power. Because then whatever that something is, that's what simplifies out. And whatever factors you have left here that didn't make it out, that's just what's under the radical. Okay? So, if I said to simplify the square root of x to the 19th power, well, we know this has to be simplified because there are more factors of x than the index, okay? So I know this can be simplified, but it's not going to go in completely, okay? There's going to be leftover factors because 19, okay, 2 doesn't divide evenly into 19. So this is what we should think of, okay? How many leftover factors of x will there be so that we hit a multiple of 2, okay? So in other words, counting down from 19, okay, what's the first multiple of 2 I would hit? 18, okay? So I want to break up x to the 19th to be x to the 18th times x to the first. So notice, it still has the same value. X, this is properties of exponent, x to the 18th times x to the first would be x to the 18 plus 1, which is x to the 19th. So now, what I did was, I broke it up because I can take x to the 18th and write that as something squared. And what squared is x to the 18th? X to the 9th. That means that this expression is the same as x to the 9th squared times x to the first. And now, if I break that up, the square root of x to the 9th squared would give me x to the 9th, and I would be left with one leftover factor of x, the square root of x. So if you can write a factor to the second power, when you take the square root, okay, it's going to undo it, leaving you with x to the 9th, and then this never made it outside because you only have one factor of x, and this is a square root. You would need 2 factors of x to simplify this. Now, what we're going to do is we're going to assume all variables are positive. If they weren't positive, okay, we would have to do things like absolute value bars on the outside to make sure that if we had an even index, that, remember we talked about the primary root, the principal root was always positive, so we would have to do some things there with absolute value bars on the outside, but we're not going to do that. We're just going to assume all variables are positive, okay? So now we're going to start simplifying nth roots with constant and variable factors. Okay, so simplify each. Assume all variables are positive. Okay, so number 1, we'll do the 5th root of x to the 10th, y to the 7th, okay? So notice, there's more than one variable factor here, okay? I've got x, I've got y. Now, this is just a product, so I could use my product property. This is the same as the 5th root of x to the 10th times the 5th root of y to the 7th, okay? And so I like to break this up. You could do this as long as it's a product inside, and now I'm just going to simplify each of them separately. So if the index is 5, okay, that means I want to write this. If I can write this as something to the 5th, if I take the 5th root, whatever is in here is what it simplifies out to be. So this is how you think about it, okay? If the index, okay, is smaller than the exponent, okay, then it can be simplified. In other words, if the exponent is greater than or equal to the index, it can be simplified. Now, you have to figure out, does it simplify perfectly, or will there be leftover factors? So, to figure out that, you take this number and you say, is this a multiple of 5? Yes, which means I can take this and I can write it as something to the 5th power. I can write this as x squared to the 5th power. So what this means is, okay, I can make 2 equal groups of x to the 5th, right? And so, if I take the 5th root of x squared to the 5th, that's just going to leave me with x squared. Now, does this need to be simplified? Yes, because there are greater than or equal to, okay, the exponent is greater than or equal to the index, okay? So next, is this a multiple of the index? No, so that means I want to break this up. So counting down from 7, you need to hit the largest multiple of the index. So the largest multiple of 5, counting down from 7. So 7, no. 6, no. 5, yes. So we're going to break this up to be y to the 5th times y to the 5th times what is the same as y to the 7th, y to the 2nd. So what this represents is the leftover factors of y, okay, that aren't going to make it out of the radical. Now y to the 5th is the same as something to the 5th power. That's y to the first. So y to the first makes it outside, and you're left with the 5th root of y squared. That's because y to the 7th is the same as y times y times y times y times y times y times y. And if you're taking the 5th root, you need 5 of the same. Okay? And you'd have 2 that were left over. And then, what's the 5th root of y to the 5th? Y. You'd be able to make one group of y to the 5th. Okay? So now, we just have to put this back together. Whatever made it outside, x squared y, and then whatever still left inside, the 5th root of y squared. Okay, so that's number 1. Number 2, we'll do the cubed root of 54, a to the 9th, b to the 2nd, c to the 11th, and we'll do d to the 31st power. Okay, so we have 1, 2, 3, 4, 5 different factors. We're going to want to break this up. Okay, the cubed root of 54, the cubed root of a to the 9th, the cubed root of b to the 2nd, the cubed root of c to the 11th, and the cubed root of d to the 31st power. Now the first one is unlike the other 4 because this is a constant factor, so you actually know what the value of the factor is. So here, okay, this is a little different than the way you do the variable factors, because here you know that if you have a factor that's a perfect cube, okay, then it's going to simplify. So what is a perfect cube that is a factor of 54? 27. 27 times 2. Okay, this is the cubed root of 27 times the cubed root of 2. The reason you break it up to be perfect cubes is because 27 is really 3 to the 3rd. Okay, the cubed root of 27 is 3. This would be left with 3 cubed root 2. But you don't look for perfect cubes here because you don't know what the actual value of the factor is. But what you're looking for is, okay, does this need to be simplified? Yes, because the exponent is larger than the index, which means, okay, I can simplify if I have at least 3 factors of a. I have 9 factors of a. So first, is 9 a multiple of 3? Yes. So that means I'm not going to have any leftover factors of a. So remember, you want this to the 3rd power because this and this cancels out. What to the 3rd is a to the 9th? A to the 3rd to the 3rd. So the cubed root and that power of 3 cancel each other out. So this would simplify to just be a to the 3rd. The cubed root of b to the 2nd, I only have 2 factors of b, and I'm trying to take the 3rd root. This does not simplify at all. There's nothing for me to do. It's just the cubed root of b squared. The cubed root of c to the 11th. I have 11 factors of c, so I'm obviously going to be able to simplify this, but 3 doesn't go into 11 evenly, which means I'm going to have leftover factors of c. So you count down from 11, okay, and you get to the first multiple, which it needs to be the largest multiple. So counting down from 11, 10, no, 9, yes. So if this is the leftover factor, okay, if these are the leftover factors, this exponent should always be less than the index, because if it was greater, that means there's more that you can simplify out. So c to the 9th is the same as what to the 3rd power? C to the 3rd. That means you're able to make 3 equal groups of c to the 3rd. Okay? So this becomes c to the 3rd times the cubed root of c squared. And then last, d to the 31st. That needs to be simplified. Okay, 31 is not a multiple of 3, so we're going to break this up. This will be d counting down from 31, so 30, so that'll be 30 times d to the 1st. D to the 30th is what to the 3rd power? D to the 10th. So that means we're going to be able to make 10 equal groups of d to the 3rd power, which means this would simplify to be d to the 10th times the cubed root of d to the 1st. So this simplifies to be 3, a to the 3rd, c to the 3rd, d to the 10th times the cubed root of 2b squared c squared d. So as long as this is a product of each of these factors, you can just break it up. Okay, so let's do another one. Number 3, we'll do the square root of x to the 5th y to the 81st times the square root of x to the 9th y to the 7th. So, notice I have a multiplication of radicals here. I'm allowed to multiply them together as long as the index is the same, and the index is the same, so I should be multiplying them together. What you have to decide here is, do you want to simplify each radical and then multiply them and then simplify them again? Or do you want to just multiply them together and simplify it once? That's what I prefer to do. It's less steps. So because they have the same index, you're allowed to multiply them together. So x to the 5th times x to the 9th, that's going to give us x to the 14. Y to the 81st times y to the 7th, that's going to give us y to the 88. So now I need to simplify the square root of x to the 14th and the square root of y to the 88th. So is 14 larger than the index, larger than or equal to the index? Yes, so that means it needs to be simplified. So x is 14, a multiple of 2? Yes, so that means I can write it as something squared. What is that something? X to the 7th. That means I'll be able to make 7 equal groups of x squared. So this simplifies to be x to the 7th. Y to the 88. Is the exponent greater than or equal to the index? Yes, that means it needs to be simplified. Is 88 a multiple of the index? Yes. So that means I can write it as something to the index. And so then the square root and the 2 cancel each other out. That would be y to the 44. That means I can make 44 equal groups of y squared. So what would simplify out? Y to the 44. So this simplifies to be x to the 7th, y to the 44th power. All right, number 4. In number 4, we have negative 4x times the square root of 20x to the 5th, y to the 2nd, times 3x squared, y to the 3rd, times the square root of 2x to the 3rd, y to the 7th. So notice, it's again multiplying two radicals together. You're allowed to do that as long as the index is the same. It is. So multiply what's on the outside. So it's going to be negative 12, x to the 3rd, y to the 3rd. And then multiply what's on the inside, the square root of 40. X to the 5th, x to the 3rd, that's going to give you x to the 8th. If you're multiplying factors that are the same, you're adding your exponents. And then y to the 9th. So what we have to worry about right now is, can I simplify that radical any further? So we're going to want to think about the square root of 40, the square root of x to the 8th, and the square root of y to the 9th. Notice 40 is a constant factor, so we think about this differently than we think about our variable factors. Square root, which means I just want a perfect square. What is a perfect square? That's a factor of 40. 4 times 10. The square root of 4 is 2. Can you simplify the square root of 10 any further? No. Okay, so 2 square root of 10 is the simplest you could get the square root of 40. Now the square root of x to the 8th. The exponent is greater than or equal to the index, so it needs to be simplified. Is 8 a multiple of the index? Yes. That means you can write this as something to the index, okay? Something to the 2nd. What to the 2nd is x to the 8th, x to the 4th squared, okay? So if you took the square root of this, the square root and the power of 2 undo each other, leaving you with x to the 4th. Then y to the 9th, yes, it needs to be simplified. 9 is greater than or equal to 2. However, it doesn't go in evenly, so you count down from 9. After 9, what's the next number below it? 8. Is 8 a multiple? Yes, so we're going to break this up to be y to the 8th times y to the 1st. Remember, this should always be less than the index. So this, what to the 2nd? Y to the 4th. So this simplifies to be y to the 4th times the square root of y. So this is now times 2x to the 4th, y to the 4th, the square root of 10y. Now, this is multiplication of this term by this term. There's not multiple terms here. this times this. There's nothing to really distribute. So multiplying one term by another, so negative 12 times 2, that's negative 24. X to the third times x to the fourth, that's x to the 7. Y to the 7 times the square root of 10y. Okay, so that's number 4. So now we're going to hit some problems that are going to challenge us in terms of knowing our rules about simplifying radicals. Okay, so number 4, multiplying. Number 5, let's do some dividing here. So we're going to do the cubed root of x to the 5th, y to the 7th, z to the 8th, over x to the 2nd, y to the 20th, and z to the 13th power. Okay, so notice we have a fraction inside of a radical. We are not allowed in a simplified expression, you're not allowed to have a fraction inside of a radical. But before we break this up using the quotient property of radicals, I would simplify as much as you can inside. Okay, this is going to simplify to be x to the 5th over x to the 2nd, that's going to give you x to the 3rd. Y to the 7th over y to the 20th, that's going to give you y to the negative 13. Z to the 8 minus 13 is going to give you z to the negative 5. So no negative exponents, so this would be x to the 3rd over y to the 13th, z to the 5th power. So now I can't simplify what's inside any further. So now I don't want to break the rule that says you can't have fractions as radicands. So we break this up. This is the cubed root of x to the 3rd over the cubed root of y to the 13th, z to the 5th power. Okay, now before you try and simplify, we have another rule we're breaking. We can't have any radicals in the denominator of a fraction. But before we get there, what we should be concerned with is, why don't we simplify each radical? So the cubed root of x to the 3rd, that's going to simplify to be x. Now, let's simplify the cubed root of y to the 13th and the cubed root of z to the 5th. So 13 is greater than or equal to the index, so it can be simplified, but 13 isn't a multiple of 3, so we're going to have to break it up. Counting down from 13, what's the largest multiple of 3 you'll hit? 12. So this is y to the 12 times y to the 1st. So what to the 3rd, right? This and this need to match, so that way if you took the cubed root, you would just be left with what's in here. That's y to the 4th. So this simplifies to be y to the 4th times the cubed root of y to the 1st, and the cubed root of z to the 5th. 5 is greater than or equal to the index, so it has to be simplified. Counting down from 5, you'd hit 3 as the first multiple. Okay? What to the 3rd is z to the 3rd, z to the 1st, so this simplifies to be z to the 1st on the outside times the cubed root of z squared. So this becomes y to the 4th z cubed root of y z squared. Now my issue here is I still have radicals in the denominator of my fraction. And one of the rules is you have to have a rational expression in your denominator. So I need to remember the only way to not change the value of the fraction, but to make it look different, is to multiply by a clever form of 1. And so let's think about what would make this rational. The denominator would be rational if this ended up being the cubed root of y to the 3rd, z to the 3rd. If these exponents were the same as this index, then they would simplify down. So, okay, I've got what this times what would get me to here. That would be the cubed root of y squared z to the 1st power. So if I just multiply the denominator by that, I need to make sure I multiply the numerator by that. Okay, and now I need to clean up my denominator here, because this is y to the 4th z times the cubed root of y to the 3rd would be y, the cubed root of z to the 3rd would be z, okay? So this is going to be x times the cubed root of y squared z all over, that's going to be y to the 5th, z to the 2nd. And now I can't do anything, my radical is just sitting in the numerator, that's okay. And just check to make sure. Notice I only have a factor of x outside and factors of y and z in the denominator, so there's nothing left for us to simplify here. This is our completely simplified expression. Okay, so let's practice one more of this type of problem. Okay. Okay, so I have the fourth root of a to the 8th, b to the 11th, c to the 10th, over the fourth root of a squared, b to the 30th, c to the 11th. So I have options here. Okay, I could simplify each radical and then see whether or not there was still a radical sitting in the denominator, okay, and I could go from there. Or if you notice, the numerator and the denominator have the exact same index, okay, and there are common factors between the numerator and the denominator. So I wouldn't start by simplifying each radical. I would start by putting the radical back together. Remember, this is just using that quotient property of radicals. And so now I'm going to simplify inside the radical first. That way, instead of having 6 separate factors, I see the factor of a once, the factor of b once, and the factor of c once. So that's going to leave me 8 minus 2. That's going to give me a to the 6th, 11 minus 30. That's going to give me b to the negative 19. And 10 minus 11 is going to give me c to the negative 1. So this is going to simplify to be the fourth root of a to the 6th over b to the 19th, c to the first power. So now I'm going to break it up. This will be the fourth root of a to the 6th over the fourth root of b to the 19th times c. So now I want to simplify each radical. So the fourth root of a to the 6th, so 6 is greater than or equal to the index, so it needs to be simplified, but does it go in evenly? No. So we have to break it up. 6 isn't a multiple of 4, so we count down. 5, no. 4, yes. So this will be a to the 4th times a to the 2nd. Okay. Now, a to the 4th is the same as what to the 4th? A to the 1st. So this just simplifies to be a to the 1st times the fourth root of a to the 2nd. All over. Now we have to see if this can be simplified. So the fourth root of b to the 19th times c. So we want to look at the fourth root of b to the 19th times the fourth root of c to the 1st. We want to look at these separately. Okay. This will need to be simplified. Is 19 a multiple of 4? No. So it's going to have to be broken up. So counting down from 19. 18, no. 17, no. 16, yes. So b to the 16 times b to the 3rd. These should always add to that. So what to the 4th is b to the 16th, that's b to the 4th. So this simplifies to be b to the 4th, the fourth root of b to the 3rd. I have one factor of c, I can't simplify this. So this is b to the 4th times the fourth root of b to the 3rd c. So now each of the radicals is simplified, but the problem is I still have a radical sitting in the denominator. And I want this to be a rational denominator. So my denominator, I need it to be, in order for it to be rational, this needs to be b to the 4th times the fourth root of b to the 4th, c to the 4th. Okay? So what do I have to multiply this by? I have to multiply this by the fourth root of, and you know that the index always has to be the same because you can't multiply radicals if they don't have the same index. So if this is b to the 3rd and you end up with b to the 4th, that means this was b to the 1st. And if you had c to the 1st and you ended up with c to the 4th, you must have multiplied by c to the 3rd. So what you do to the denominator, you must make sure you do to the numerator so you don't change its value. So this is going to give you a times the fourth root of a squared b c to the 3rd. Okay, so now we have to clean this up because this is now a rational denominator. So this is a fourth root of a squared b c to the 3rd all over b to the 4th times the fourth root of b to the 4th is b, the fourth root of c to the 4th is c, so it's going to be b to the 5th times c. Now look, The radical's completely simplified. You have 2 factors of a, 1 factor of b, 3 factors of c. It's okay, it's sitting in the numerator. You have a factor of a sitting on the outside here, and you have factors of b and c in the denominator, so there's nothing to simplify outside. So this is the completely simplified expression of number 6. So make sure, remember, we're assuming all variables are positive, and make sure you have completely simplified each expression. So now we know how to simplify nth roots when we have constant factors as well as variable factors.